Section 8.3 is all about applications to physics and engineering. We are going to talk about two specific applications. That's force of a liquid and centroids, centers of mass. So force due to water pressure, better way of saying it. There we go. So deep sea divers realize that water pressure increases as they dive. That's why they have to come up slowly. And if you've ever been in a pool, you realize that the pressure changes the deeper you go. So, fluid directly above a plate that has volume A times D, where A is the area and D is how thick it is. So its mass is density times volume, which would be rho times A times D. The force exerted on the plate is equal to mass times gravity, the amount of gravity coming down. So pressure, and it's measured in pascals, and that's such a small number that we usually use kilopascals. So for instance, because the density of water is 1,000 kilograms per cubic meter, the pressure at the bottom of a swimming pool that is 2 meters deep is 1,000 times 9.8 times 2, which would be 19,600 pascals or 19.6 kilopascals. We're going to be looking at the hydrostatic pressure on the side of the pool, or a dam, or a gate, or a trough, just anything that's holding water. An important principle is the fact that water has the same pressure in all directions. You feel the same pressure on your head as you do your feet if they're at the same depth. But remember what we said, pressure is not constant, so it's going to change as we move up the side of the pool or up the side of the dam. So our procedure is first we draw a set of axes, and I like to draw it on the y-axis. You can switch it and make the x-axis if you want to, on the face of the dam, and you choose a convenient place for your origin. Usually at the bottom of the dam. If you have a circular gate that you want to calculate the pressure, you might put it at the center. Then you find a function, W of y, for each y on the face of the dam. So you're going to calculate a function for the width of the dam. And then you put the integral from the bottom of the plate to the top of the plate, because that's where it's feeling pressure, rho times G, so the density of the water or whatever liquid, gravity. Then you have A minus Y. So A starts, in this case, at the top of the water, minus Y, times the width at each Y. So let's do an example. A dam has the shape of a trapezoid, shown in figure 2. The height is 20 meters, the width is 50 meters at the top and 30 meters at the bottom. We want to find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So I'm going to draw a picture. First, I start with a set of axes. And I'm going to put the middle of the dam at the center. So it's 30 meters wide at the bottom, so it would be 15 over here and 15 over here. It is 20 meters high, so I'm going to call this 20 meters. So this would be 50 meters wide at the top, so we have 25 here and 25 here. And let's go ahead and label this as 20 meters tall. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top. So water's not all the way up to the top. Water's right here, 4 meters. So this is actually 16. So we have 16 meters of water, but our dam is 20 meters tall. Now we need a function for the width. That's the most challenging part of these problems. I'm going to draw this little triangle over here, and I'm going to separate it out. I know how tall the triangle is. It's 20 meters tall. Now, it's 15 meters from the origin to the base, the edge of the base, and it's 25 meters from the origin to from the y-axis to the edge at the top. So that means the length here is 25 minus 15, which is 10. Now, for every point let's put xy up here. We have a triangle. The height of the triangle, and I'll copy it over here, is y. The width of the triangle is going to be x minus 15, because it's 15 units to get over here to where the triangle actually starts. So now I have some similar triangles, and I can do 10 over 20 has to be equal to x minus 15 over y. Now remember, I want functions of y. So 10y is equal to 20 times x minus 15. So let's divide both sides by 20. 1/2 of y is equal to x minus 15. So 1/2 of y plus 15 is equal to x. So x right here is equal to 1/2 of y plus 15. But the width of my trapezoid is 2 x's, because it comes from negative x all the way over to positive x. So width as a function of y would be equal to 2x, which is 2 times 1/2 of y plus 15, which would be y plus 30. Now let's talk about our limits of integration and our depth. We integrate from the bottom of the water to the top of the plate that is underwater, because there's only pressure where there's water. We're trying to figure out the pressure. So 0 to 16. Then we have rho times g, and we're in meters, so I'm going to go ahead and multiply 9,800, 1,000 times 9.8. My width is y plus 30, and then we take the top of the water line, wherever that is. In this case, it's 16 minus y. So in this case, our limit of integration and our depth had the same number in them. If the water level is above the dam, then that can change. But I'll take a minute and do the integration. And since this is the pressure against the entire side of the dam, our measurement, our units are in newtons. because it's over the entire area, not per square meter. Let's look at example 2. This time we have the hydrostatic force on one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. So our limits of integration are going to be different than our depth because the water is above the edge of our drum. Now I notice that the picture I have drawn here has the center of the drum at the origin. So let's draw our picture just like this one. This is example 2. I draw my axes. I do my best to draw a circle. And the radius is 3 feet. So x squared plus y squared equals 3 squared. I need a function for the width. So the width of this thing goes from negative x to x. So width again is equal to 2x, and we want width to be a function of y. So x squared is equal to 9 minus y squared. So x is plus or minus square root 9 minus y squared. And since we're thinking about distance, our width is 2 times the square root 9 minus y squared. Now we think about this is 3, this is negative 3, this is positive 3, this is negative 3. And it says that it's submerged in water that is 10 feet deep. So if this is the bottom of the water and the drum is sitting there on the bottom, we've got 3, 6 feet, but it's 10 feet of water, so there's another 4 feet that lives above the drum. So the water level is at 10 feet. So we have our width, and we have what we need to figure out our depth and our limits of integration. And I'm going to have to peek because I forgot to type in what we're using for the density of water, 62.5. I don't have that one memorized. 62.5, and we don't have to do anything with gravity because we're using pounds, and pounds includes gravity. So we're integrating from the bottom to the top of the plate that is underwater. So negative 3 to 3. The width is equal to 2 times the square root of 9 minus y squared. And then our depth is going to be the top of the water. And that's not 10 feet. We want 10 feet. That would be 3 plus 4. That's 7. It's at 7. Because the water's 10 feet deep, but 3 feet is below the origin, below the x-axis. So 7 minus y dy. And you know how to integrate, so we're just going to scroll down, and there's your answer. Now, if you don't like having to have your numbers go negative down below the axis, you can always draw the bottom of your drum at the origin. Now, if you have the bottom of the drum at the origin, then your limits of integration are exactly what you want them to be. It's 10 feet, 6 feet, because the radius is 3, 3, and here is 0. And you have to think back to your pre-calculus where you learned how to write down the equation for a circle whose center lives right here at the point 0, 3. It's x minus 0 squared plus y minus 3 squared is equal to 3 squared. That's the only difference in the formula. So if you put your center at the origin, your formula's a little bit simpler. We're plugging it into a calculator, so who really cares? So now we have that x is equal to plus or minus, we'll go ahead and give it its plus or minus 9 minus y minus 3 squared. So width is still 2x, so it's 2 times the square root of 9 times y minus 3 squared. So force is equal to the integral from 0 to 6 this time, because that's the boundaries of my plate that's underwater. And we said it was 62.5 pounds. 2 times the square root of 9 y minus 3 squared. And now the depth is, the water's 10 feet deep. So 10 minus y dy. And you'll notice that I did it both ways because I think it's fun to show that either way you come out with 12,370 and your units are pounds. So American Standard units are pounds for force. Units in metric are newtons. Try this one on your own. You have a vertical plate submerged in water and it has the indicated shape. Express the force as an integral and evaluate it, and you can use 62.5 pounds for the density of water. Did you get it? Let's look at it. So I did similar triangles. This time your similar triangle lives up in the top of your big triangle. Now if you don't like similar triangles, you could have just looked at the point right here, which would be the point 0 and it's 5 feet tall, and the point 10, 0. Slope is equal to the change in the y's, so 5 minus 0 over 0 minus 10, which is negative 1/2. So y is equal to negative 1/2 of, we don't even need to do y minus your y coordinate. We know the y-intercept, so negative 1/2 x plus 5. I have y equals negative 1/2 x plus 5, so y minus 5 is negative 1/2 of x, so negative 2 times y minus 5 is equal to x, so 2 times 5 minus y is equal to x, which is exactly what I have down here. So you can figure it out either way. And then we do our integrating. We go from 0 to 5 because that's the bottom to the top of the plate. And then the water level is 7 minus y, and this was our width right here. Got another practice for you. This one's partially submerged, so it'll be a little different. Give it a try. I'm hoping you didn't try to do this integration by hand because it requires trig substitution and you end up having to take the arc sine of 2/3 and it's not a simple one. So I would just plug this one in the calculator for sure. I put the center of the bottom of the semicircular plate at the origin. So x squared plus y squared was 6 squared, since it was 12 meters in diameter. So the width is 2 times the square root of 36 minus y squared. We have meters, so I know it's 9.8 meters per second squared for gravity and 1,000 per cubic meter for kilograms per cubic meter for density. So width and depth are the same because the water level is below the top of the plate, and we only go from the bottom of the water to the top of the water because that's where the pressure is. So force problems, not so bad. Remember, the units are newtons or pounds.